So we go on with our tutorial with Apoferritin using Scipion3. So the next point is we have at this level we have chosen our particles in 2 dimensions, and we have extracted them at the size that we think we will be able to reconstruct with accuracy, and we have an initial volume at that size. So let's look at the initial volume, how it looks like. So this is we can see actually the window outside, and we can see in 3D if we want. For some reason it doesn't like. Some of them they don't like, some of them they like. Okay, but the point is that we have an initial volume, we have a set of particles of that size, and we have inverted the contrast so that the particle looks like white on a darker background, and then the next point will be trying to make a cleaner 3D reconstruction, and also a 3D reconstruction of a population that we think it is purely consistent with one single structure. So we will start by refining this input volume. So this is done in this refinement tab or menu. So we have refinement from XMIP, from Relion, from CrySpark, from Iman. So I have used the one from CrySpark. It is very fast. And this one here, the main parameters are, which is the input particles, which is the set of volume, which is the volume, and then otherwise what is the symmetry. But otherwise, all the remaining parameters normally you don't have to touch. You can optionally give a mask. I don't recommend it at this point because it may remove artifacts that are actually present, but because of the mask they are hidden, and then it is good, I think, a good thing to not provide a mask during the process, just to be able to recognize these pathologies. Sometimes if the set of particles is very difficult to align, then you may need the help of the mask to be able to align the particles to the 3D structure. But otherwise, in general, I would discourage the use of a mask here, because it artificially inflates the Fourier shell correlation, and it also hides artifacts that are present, but they are hidden by the mask. Okay, so let's look at the results. So we can look at all the FSCs. So this is the first check to look at. So what we have here is that without a mask it gives a resolution 3.3 angstroms, the maximum resolution, but this is with different kind of masking. So the problem with masking is that it artificially inflates the Fourier shell correlation. It may inflate artificially the Fourier shell correlation. It doesn't mean that all masks are nonsensical, but there is a severe risk of inflation. But still we see that the resolution is somewhere between what we expected. So somewhere between 3 and 2 angstroms, in this case 2.8 angstroms. And then we can look at the volume. So let me look at the volume by slices first. This is where you can see the artifacts. So artifacts normally they are manifested in stripes or strange structures outside your particle. So here we can nicely see the particle, but and we don't see anything in the background. So it is just noise what we see in the background. So that means that at least at this level we cannot see any important artifact. And then we can look at it in 3D. Now it likes, and we can nicely see some of the alpha helices, and we see these four corners that I was referring to before. So these four corners in the structure of the Apoferritin. Okay, good. So now this is the first reconstruction, and we might stop here, but actually we don't want to stop there, because at this point we have taken a set of particles, an initial volume, it has nicely converged, but we don't know if really all the particles that we have used for the 3D structure, they are really consistent with that structure. And the other thing is that we don't know whether the parameters of those particles have been correctly identified. So let's solve first the first problem. So the first problem is, do all the particles belong to that structure? And for that, what we will do is a 3D classification, and we take the set of particles coming out from the previous step, and we will try to classify it. So you need here an initial volume, and we will take the one coming from CryoSpark, and because we think that that volume is not biased, but it really it faithfully represents our structure, we will filter it at 15 angstroms only, and then we will do an optimization that will try to separate those input images into two separate classes, and this is what we get. So now we see that we had 3,000 particles, around 3,000, a bit more than 3,000 particles. We see that most of them, they go to a class, but a fraction that is around 20% of them, or something like that, around 20, I think, it goes to a structure that is really not the right one. So we can see that there is an important mistake in this structure. So that means that in the 3D reconstruction that we had above with CryoSpark, we have a mixture of these two structures. So this second structure might be particles that have been misaligned, or particles that whose center was really off-centered, and then they cannot be correctly aligned with the volume, or it can be particles in some other conformation, or they can be alignment mistakes, 3D alignment mistakes. So they can be many things, but they cannot be safely aligned to the input volume. And if actually particle classification is a relatively unstable process, so if you repeat the process twice, you are not guaranteed to get twice the same answer. So here what we see is that more or less we get similar results. The two volumes look more or less like the previous ones, the number of particles too, but actually if we compute what are the intersections between the different classes, we see that not all of them were assigned to the same particle. So let's look at this again. So this was one of the results. This was the other one. So let me go to this one. So we see that in the two classification processes, 2400 of the particles went to the correct class, or at least they go to a class that we can easily recognize. But the problem is that they are not the same 2400 images. So that is what this other algorithm is computing. Only 2000 particles were consistently assigned to that class. The remaining particles in the original classification, so these 400 extra particles, they are somehow in the other classification, they were sent to the wrong class. So that probably means that those are images for which the class cannot be safely be determined. So sometimes it is assigned to the good class, sometimes it is assigned to the bad class, and actually you are not sure what that particle is. It could be a particle for which that was in a nice area, that was not that was thicker than the rest, so it cannot be the particle itself cannot be so easily seen, or it has very low contrast, or it has some particle on top, or it has whatever problem that doesn't allow the particle to be confidently assigned to one of the classes. So again, if you don't have any one of these consensus tools, you are not able to recognize all these particles, and they are all doomed to be thrown into one of the classes, and you will be forced to accept all of those as correct images, while you are not so sure about that. Okay, so now we have 2000 particles. Those are the 2000 particles that were consistently assigned to the same class, and you can repeat actually this process a few times. These consensus classes in 3D can take multiple outputs, and it will separate only those images, those subsets of images that were consistently classified together. And then so we have here these 2000 particles, and now we believe you could keep on cleaning and cleaning further and further, but let's for this tutorial let's try to keep the workflow simple. So at this point we will not clean further. You could try, but actually in this particular case it doesn't separate the images anymore. So now with these good particles and this initial volume that was a correct one, then we will do another refinement step. One will be with CryoSpark, and again we can look at the CTF. So the CTF goes more or less to the Fourier correlation goes more or less to the same point. It was before 2.8, but here it is 3 angstroms. There is not really a big difference between 3 and 2.8, and now we have the advantage that we are sure that the particles that we are putting in are the right ones. And also we can look at the volume, the reconstructed volume, and well, it looks more or less as before, but again now we are more sure that the particles we are putting in are the correct ones. And we can repeat the same process, but now with Relion. So Relion, again, the main parameters are the same as before. So set of particles, what is the reference 3D map, what is the symmetry, and because we trust our previous map, we don't need to filter it much, and that is basically it. And this parameter may be important also if there is a previous alignment. Or you can start with finer sampling, angular sampling steps, and when you want to go to very high resolution, then typically you start decreasing this value and this value. This is the same, the sampling for the degrees. So it starts with this initial sampling, and then it does only a local search when it reaches this level of 1.8 degrees. So from 7.5 to 1.8, in principle it is doing global searches of the angular assignment, and this also can help a lot to constrain the search of shift in this case. Yeah, that's it. So now we have let's see the FSC. So the FSC probably it is not this one. So the FSC looks more or less like the one of CrySpark without masking. Yeah, and I more in favor of looking at FSC without the masking, because otherwise it is really can really bias a lot and inflate a lot the Fourier shell correlation. And then here we will look for the final volume. So this is how the final volume looks like. So for some reason it doesn't show correctly. So the final volume doesn't look good, but the halves probably they look much better. So in principle, this is some particular mistake of this data set or this execution. The half maps look good. And they look more or less, we can compare it to the one of CrySpark. So for instance here we have the same map, and we have to go to similar slices. So let's say this is a slice 98, so here we move to a slice 98 too. And there is a so this is very subtle, but sometimes, and this is one of the cases in which on top of the structure we see kind of haze in the case of Relion, and sometimes it is in the case of Relion, sometimes it is CrySpark, sometimes it is whichever other program, but this haze are on top of it typically is coming from badly aligned particles. And these badly aligned particles are smearing out in the 3D process because they are average, but the average is not zero. It is different from zero, and this is this low frequency signal that is on top of our 3D structure. So to identify those badly aligned particles, what we can do is to compare the angles between the angular assignment of Relion and the angular assignment of CrySpark. In this particular case, it has octahedral symmetry, so we don't have to align the volumes. If it is a C1, an asymmetric structure, then the two volumes may be in relatively different positions, so you may have to align the particles and the volumes. There is an algorithm, a protocol for that. Actually, if you press Ctrl F, you are able to look for something, and then here you have align volume and particles. So you would align the volume and particles from one to the other one, so that then you can compare the angular assignment. Then we will compare the angles, and the input for this is the angular assignment of one of the algorithms, the angular assignment of the other one, and then the symmetry, and then you get this kind of results. So you have for every particle what is the angular difference and the shift difference, and originally they are shifted, they are sorted by angular difference. So you can make a sort and see what is the plot of angular difference between the two, and you can see that there are angular differences that are y is the angular difference, so most of them are within 1 degree of error in the 3 Euler angles. So this is the average of the 3 Euler angles, so most of them the angular error is below 1 degree, but for a few of them it is much bigger than 1 degree. So those are the particles whose angular assignment you are not so sure. So you can take them off. So you can go to, for instance, let's say 1 degree if you want, and say, okay, so from 1 degree on, I will select from here and disable. And now you sort by the shift, and you can make a similar plot with the shift. And again, you see that most of them, they have a shift that is consistent with each other in more or in less than 1 pixel. But then for some of them, there are significant differences in the shift. So you don't know which one is correct, but what you know is that at least one of them is incorrect. So you may again go to one. So you see, those are the ones that are very much shifted, and those were particles that were off-centered when picking. And then you may go to 1 pixel, select from here, disable, and then you produce a new set of particles that are the ones whose angular assignment is consistent between 2 algorithms with different implementations and following in principle different mathematics. So this is what I did. So I chose those images that had an error, an angular error smaller than 2 degrees and less than 1 pixel, and then I enter into high res. High res is the angular assignment algorithm of XMIP, and you can use it in many ways, but the way I use it in this case was I chose these images. I chose one of the 3 reconstructions, and then you can use this particle size to constrain the search of angles and shifts, but not the 3D reconstruction. So this is done only for the angular assignment, and then I used the local assignment because I had a previous estimated assignment from the consensus of these CryoSpark and RelyOn, and then I looked for the shifts and angles. You can also go further and refine the scale, the gray values, the default key, whatever. But in this particular case, in which we have so few images, probably this is not a good idea, because you need more data to make sure that what you are correcting is actually significant. And then the output of this has this FSC. This FSC high-res is fighting noise a lot. So outside the structure, it identifies those areas that are candidates to be noise, and they are dampened. And so these, so the 2 halves are very consistent with each other, but it doesn't mean that we really have this extremely high resolution. Actually, the resolution in high-res, typically it is more related to the one with the crossing of 0.5, so in this case around 3.2, but but this is without any masking at all, and you can compare to this one, in which the crossing with 3.5 was also earlier, so it was around 4. So if we compare same thresholds, high-res does not compare badly to those. And we can look at the volume. The volume looks now very good, so we don't see this haze on top. And the background noise, you see that it looks differently from the one from RelyOn and CryoSpark. The reason is this fighting noise that I mentioned before. And if we look at the 3D structure, we see many more details than we were able to see before, despite the fact that the nominal resolution is still more or less the same. But you see that these alpha helices, they are much better defined than we had before. But it is not only the merit of high res. So it is the merit of high res, but also the merit of these making sure that the particles that are put in are those that are consistently assigned to the good class, and this consensus of angular assignment parameters. And something else that we can also look at is these output particles. So the output particles in high res, you can look at when you do the local resolution, the local refinement, you can look at the coast, and you can look at the histogram of the coast, and you should see a single population. Sometimes you see that in this point that you have a mixture of populations, and then you have to separate them. But in this case, we have so few particles, and they are so consistent to each other that we have a single population here. And you should also look at the angular assignment. So the angular assignment should be more or less well spread in the projection sphere. So you can do it with these heat maps, or you can do it with these plots. So ideally, you should cover the full sphere. The fact that you don't have any particles in this area is because of the octahedral symmetry, so you don't need to cover the full area, because every particle has 4 or 8 equivalents. I don't remember for the octahedral symmetry, but it has a number of equivalents, so that everyone is replicated in the projection sphere. So, but within the asymmetric unit, you should cover it as well as possible, as homogeneously as possible. So it is not perfectly homogeneous, but it is not bad either. Okay, so then those are the verifications that we can do at this point, and in the next video we will do further verifications and further refinement of the 3D structure.